Good afternoon, all. Welcome to my talk. My name is Sunish Kumar Orappanpara Soman. I am working as a lecturer in Ulster University, Belfast, UK. First of all, I would like to thank Professor Wang and other coordinators of this conference for inviting me for this talk and giving me an opportunity to present my work. So the title of my talk is Perturbation Theory Based Learned and Non-Learned Fiber Nonlinearity Compensation. So in this talk, I would like to introduce or discuss some of the basics of the learned and non-learned perturbation theory based fiber nonlinearity compensation. So here learned means the machine learning or deep learning based approach, and non-learned means the traditional or conventional perturbation theory based fiber nonlinearity compensation. So this is the outline of my talk. We start with the introduction. Then we discuss the traffic evolution in data networks in general and in optical networks in particular. Then we talk about the digital signal processing techniques for fiber nonlinearity compensation. We mention benchmark or traditional fiber nonlinearity compensation technique called the digital backpropagation. Then we discuss the non-learned and learned perturbation theory based approaches for fiber nonlinearity compensation. So 2023 is kind of a special year for optical communication engineers and scientists. We are celebrating 50 plus 3 years of light speed connections. So during 1970s, two breakthrough technologies have been invented, that low-loss optical fiber and the room temperature semiconductor lasers. Those were the reason why we see this much development in the communications all over the world, or the global communications, and these inventions actually enable the light speed connections across the continents and the oceans. So this is a screenshot of the submarine cable map, and this is updated on February 22nd of this year. And this is the place I am sitting now. So we can see that a bunch of optical fibers are, under the ocean that connects the, continents altogether. So a huge amount of data has been transmitted through the optical fibers. So, in every point of time, we are actually utilizing the buried or existing underwater optical fibers for transmitting or receiving data. So for example, if you want to access a bit of information from another country or a continent, you need to use optical fiber for this long distance data transmission. So optical fibers are kind of very important for modern communication systems in general. So, but the optical fiber has several linear and non-linear effects that affects the signal quality when you transmit it over long distances. So here, this figure shows the evolution of optical networks right from 1980s and until 2040, kind of an prediction. You can see here various technologies have been used time to time to increase the capacity of optical fiber. So right now around here, we are actually in the verge of the capacity limit of single mode optical fibers because of the huge nonlinear effects, and also the possibility of fiber fuse if you go for capacities beyond 100 terabit per second. So the current technologies are looking for solutions for compensating fiber nonlinearity, or even some other researchers are going on to develop new multiplexing technologies and new fibers. For example, the multi-core fiber, multi-mode fibers, or even the hollow core fiber. Those were the new fiber types that can be used for huge data transmission over long distances. So the demand for transmission capacity always increases. So we have to use all the available degrees of freedom to increase the capacity. It can be in the terms of using new optical fibers or new techniques for multiplexing, or new techniques for compensating the fiber nonlinearity. So as capacity increasing, the nonlinearity is kind of limiting factor that puts a cap on the maximum achievable capacity. So this figure shows the an example of different degrees of freedom we can use to increase the capacity or meet the demand of capacity or increasing capacity demands. You can either use optical super channels, multi-level modulation formats, space division multiplexing using multi-core or multi-mode fibers, or ultra broadband communication using combining the C and L bands in the WDM system, expanding the current C band to the other bands. However, whatever the techniques we apply, the fiber nonlinearity puts a cap on the maximum achievable capacity. As you increase the transmission capacity or transmit launch power, fiber nonlinearity becomes the limiting factor, especially fiber kerr nonlinearity. So this block diagram shows several linear and nonlinear effects in optical fiber. You can see here these blue shaded blocks are the nonlinear impacts or nonlinear effects. We call Kerr effect. We have self-phase modulation, cross-phase modulation, cross-polarization modulation, and four-wave mixing. And we have other linear and inelastic scattering effects as well. So in my talk, I'm concentrating more on the Kerr effect compensation. Kerr effect is an intensity dependence of fiber refractive index. As you increase the transmit power, the Kerr effect comes into play. So we have published one survey paper and also one tutorial paper exclusively on fiber nonlinearity, its physical meaning, and also the we reviewed various DSP techniques in literature for compensating fiber nonlinearity. If you need more details, you can go through these publications. One in IEEE Communication Survey and Tutorial, and one in IOP Journal of Optics. So this is a well-known Shannon capacity equation. You can see here, we can use several degrees of freedom to increase the capacity. So, however, if you increase the transmit launch power, overall launch power, the fiber nonlinearity comes into play. So here you can see that the optical signal to noise ratio, that is the ratio between the optical power to the noise power, you can see that the we have the noise from the AIC noise, that is the linear noise from the EDFAs or optical amplifiers. And we have the nonlinear noise from nonlinear effect or the Kerr effect. So this actually increases as you increase the launch power. So essentially what is happening is that your signal to noise ratio, it is directly connected with OSNR. If OSNR decreases, signal to noise ratio also decrease. So your capacity decrease if nonlinear distortion increases. So this is a pictorial representation of the capacity. As you increase the signal to noise ratio or power, transmit power, at some point, at some optimal power, the nonlinearity effect kicks in, and essentially your capacity start decreasing. So our aim is to use DSP techniques to reduce the variance of this nonlinear distortion, and somehow applying the DSP techniques to improve the capacity curve, something like this. We can shift the optimal point further to the nonlinear regime of the optical fiber. So here we talk about the traditional DSP-based approach for fiber nonlinearity compensation before going to the land and non-land perturbation-based approach. So this is again a well-known equation called the nonlinear Schrodinger equation. So this is an elegant equation. This equation tells you the evolution of signal or electric field in optical fiber. This is a simplified form. We have this representing a single polarization optical fiber signal transmission. Here we have the dispersion and the nonlinearity. Dispersion is the linear effect, and this is a fiber nonlinearity. So here beta 2 is the dispersion coefficient, and gamma is the nonlinearity coefficient. So as we have seen in the previous block diagram, there are various sources of nonlinearity like self-phase modulation, cross-phase, and four-way mixing are the nonlinear effects. So here, this equation, in two conditions, we can have the exact solution. We can solve this, this nonlinear Schrodinger equation for two cases. Either dispersion is zero or either gamma nonlinearity is zero. However, in practical case, both effects are present. So this equation is, we cannot solve this equation exactly. So in that case, you have to use numerical solutions like split-step Fourier method for solving the nonlinear Schrodinger equation. So the nonlinear, the split-step Fourier method is actually a method which divides the fiber into several slices, and if you model the dispersion effect and nonlinearity effect separately, basically this is kind of a computationally intensive approach. So in when it comes to the compensation, by following the same approach of split-step Fourier method, we can design a DSP approach called digital back propagation. So in this nonlinearity compensation technique, we digitally propagate the received signal through a virtual inverse fiber model. So this inverse fiber or the fictitious fiber model is digitally modeled using the split-step Fourier method approach. And this is a forward propagation. When you receive the signal, we digitally back propagate signal from the receiver to the transmitter to estimate what you transmit at the transmitter. So this follows this split-step Fourier method approach. As we mentioned, this is computationally intensive. So for higher accuracy, you need to have large step sizes in the split-step Fourier method when you implement it for the compensation. So because of the huge computational complexity, the practical application of this digital back propagation is very limited, and it is not interested by the industry. So this is the reason why people look into the approximation methods or mathematical approximation method to solve the nonlinear Schrodinger equation. So perturbation theory is one such method. This is an analytical approximation method. We can use approximately solve the nonlinear Schrodinger equation. So here we talk about the traditional perturbation theory based approach for compensating the fiber nonlinearity, and also some of the recently proposed machine learning based or perturbation theory based machine learning approaches to compensate fiber nonlinearity. So the idea of perturbation approach is like the solution of nonlinear Schrodinger equation can be expressed as a power series in nonlinear coefficient gamma, and we can write the solution or output of the optical fiber or of output optical field in the form of a power series. And first term is a zeroth order term that corresponds to the linear solution. That means non-linearity. And second term is the first order correction, and second term is the second order correction, and so on. So in our approach, we limit to the second order, and we compute the distortion field using the first order perturbation solution and the second order. So our contribution was we extend the first order theory to the second order, and these are the set of equations we obtained by solving nonlinear Schrodinger equation using the perturbation approach. So this is the expression for the zeroth order field, and this is expression for first order field, and this is the second order field. So this is a summary of what we model or how we use perturbation theory to solve the Schrodinger equation. So this is the Schrodinger equation representing the signal evolution through the optical fiber. And one another technique we came across while developing the second order theory, this was kind of a byproduct we obtained while deriving the second order field. That technique is called enhanced perturbation based approach. That is, if you use a first order perturbation, you know that when you truncate that series, perturbation series to the first order, there is an approximation error is basically overestimate the distortion power. So by using a simple trick called an enhanced perturbation, we can improve the accuracy of that perturbation approximation if you limit to the first order. So here you can see that we have the 0th order and only the first order. By applying the enhanced perturbation, we can improve the, the quality of the nonlinear distortion field we calculate using the first order theory. And continuing with that, we extend to the second order perturbation. So these are the set of equations for solving the second order field. So we actually add one more term to the perturbative solution of the output field. Thereby, we improve the accuracy of calculating the distortion field or the signal field at the output. So you can see here, this is a plot showing the maximum reach versus the launch power for various techniques we have considered here. We can see that this blue curve is our enhanced perturbation, and we can see that it has a considerable gain in terms of the maximum reach compared to the linear solution. And we also included the results for digital backpropagation for the comparison. And here you can see for the second order, we have further improvement in the transmission reach compared to the linear compensation. So these results are available in two publications, IEEE Photonics Journal and one in Journal of Light Wave Technology. If you need more data or more information, you can refer these two publications. So here we talk about the machine learning based approaches used in nonlinearity compensation. So as I said, this equation is essentially the first order correction or first order solution. Here we have triplets. This is something, this is how the input pulses are interacting nonlinearly. So this equation tells us, the how distortion field generates because of the nonlinear beating between the triplet pulses, and this is the coefficient called nonlinear coefficient or perturbation coefficient, that actually the coefficient of nonlinear beating. So in this approach, we use these triplets as input feature to the deep neural network, and deep neural network basically estimates the nonlinear distortion field and subtract from the input signal for compensation. So in our approach, we extend this idea to the second order. We use two DNNs like this. So the second DNN we use for compensating or estimating the second order perturbation field. So here you can see that the inputs are triplets for the first order DNN, and here the inputs are the Q tuples instead of triplets. We have 5 pulse interactions. So if you give these as input features, and this network estimates the first order and second order distortion field and subtract from the input signal for the compensation. So this is the some result for this our proposed approach. You can see that the second order approach somehow approached the digital backpropagation technique with reduced complexity. So here, this is one of our latest work. In the previous work, or the existing DNN-based approaches, which uses perturbation theory or perturbation model, they estimate, they compute the nonlinear distortion field by inputting the triplets as the feature, and triplets are computed traditionally using mathematical computation. So that actually increases the complexity of overall complexity of using the DNN approach. Here we propose a new approach where we estimate the nonlinear, the feature or the input feature using a machine learning approach using a RNN from the received samples or symbols. Then we feed this as input feature to the deep neural network to estimate the nonlinear distortion field. So in this approach, we use a GRU bar LSTM for estimating the triplet-like features and input to the DNN to estimate the nonlinearity. So here the result shows that our proposed approach, this fully learned PBNLC, outperforms all the existing DNN-based approaches in the literature. So for more information, you can go to these publications. And this is all about my talk. Thank you so much for your attention, and have a nice day. Thank you.